ናሽናል አቪዬሽን ኮሌጅ የናሽናል ኤርዌይስ እህት ኩባንያ ጥራት ባለው ስልጠና ልዩነት መፍጠር ዋናው ዓላማው ነው። ከከፍተኛ ትምህርት አግባብነትና ጥራት ኤጀንሲ ሙሉ ዕውቅና ባገኘንባቸው በማስተርስ ፕሮግራም ኤምቢኤ በስትራቴጂክ ማኔጅመንት፣ ኤምቢኤ በቢዝነስ ሊደርሺፕ፣ ኤምቢኤ በሪስክና ኢንሹራንስ፣ ኤምቢኤ በባንኪንግና ፋይናንስ፣ ኤምኤስሲ በኢንተርናሽናል ትሬድና ኢኮኖሚክስ፣ ኤምኤ በሆስፒታሊቲ ማኔጅመንት፣ ኤምኤ በሎጂስቲክስና ሰፕላይ ቼን ማኔጅመንት፣ ኤምኤስሲ በአቪዬሽን ማኔጅመንት ተማሪዎቻችን በልዩነት ይማራሉ። በኬንያ ሀገር ከሚገኙ ስመጥር ዩኒቨርሲቲዎች በመጡ ፕሮፌሰሮች ስልጠናው ይሰጣል። ናሽናል አቪዬሽን ኮሌጅ በዲግሪ ፕሮግራም በአቪዬሽን ማኔጅመንት፣ በአካውንቲንግና ፋይናንስ፣ በማርኬቲንግ ማኔጅመንት፣ በሆቴል ማኔጅመንት በምዝገባ ላይ ነን። በአጫጭር ኮርሶችም በፍላይት ኦፕሬሽን፣ በቲኬቲንግና ሪዘርቬሽን፣ በሆስቴስ፣ በሆስፒታሊቲ ማኔጅመንት እናሰለጥናለን። አድራሻ ከ22 አደባባይ ወደ ሾላ በሚወስደው መንገድ ላይ ናሽናል አቪዬሽን ኮሌጅ የናሽናል ኤርዌይስ እህት ኩባንያ ህልሞን እውን ያደርጋል።
ሰላም አላችሁ።
እግዚአብሔር ይመስገን።
ሰብለ ወንጌል፣ ጤና ወርቅ፣ መሳይ እንደምን አላችሁ?
ደህና ነን። ሰላም ነው ዶክተር።
So today, last week, we already started chapter 4 and we learned about 30% of the chapter. Today we will try to wind up this chapter and we will make ready ourselves for the next chapter, maybe by tomorrow or other days. So last week we have covered some of the contents of chapter 4 and we discussed up to slide 27. And to remind at least the last topic we have discussed, we already start how to assess the uncertainty of y, or how to assess our dependent variable in regression model, or we can say our performance indicators. So we say there are several approaches to measure the uncertainty of y, or to assign probability for y. We focus on these three of them. The first one is it's based on classical statistics, and second one is about judgment of the uncertainty of y based on the available information. And the last and the most important approach is using expert elicitation. And we already learned about classical statistics approach to assign probability for y. So today we will continue the second approach to assign or to judge the uncertainty of y or performance measures. That is the so-called using all sorts of information to judge the uncertainty of y. Now, this approach compared to the other two, the classical statistics and the expert elicitation, this approach is the most widely used or most commonly used in risk analysis. And this method is used when data are absent or when we have only partial information which is relevant to the assessment of uncertainty. So the most important criteria to use this approach, the approach called judgment using all sorts of information. This method we adopt when data are absent or are only partially relevant to the assessment of uncertainty. So if you don't have data, we will rigorously or in depth use the what if assumptions. Or we have data, but this data is not completely relevant for the assessment, but it used only for it have partial relevance for our objectives, right? So in this case, the responsibility of summarizing information required to assign a probability, writing the rationale or giving rationality, and specifying the probability distribution rests on the risk analyst. So when we use all information for the judgment of uncertainty Y, all responsibilities is given for risk analyst, right? Risk analyst. And it's all about subjective approach because we don't have data. In the situation we have subjective approach, if there is two risk analysts, there is big probability this analyst come up with different conclusions or different assignment of probability for a given uncertainty, right? A given uncertainty. So the question, if it is it is subjective, and two different analysts come up with different probability assignment, the question would be, how does the analyst arrive on one particular probability distribution, right? This is the question we have to address. So in order to address this question, let us take two scenarios. The first scenario, assume the distribution of our observation is binary. It takes, or the value of Y is between or 0 and 1 only, which means binary response, right? Binary response. And then based on this distribution, we are going to specify the probability of Y to be 1. That is success, right? That's success. And 0 failure, right? 0 failure. So we assume the analyst or the risk analyst has, or he or she have a good experience in assigning probabilities. So based on his experience, he may refer different referencing points to assign the probability of success or for the probability of failure, right? Probability of failures. For example, if you assume the experience has good, the analyst has good experience, he may feel what 0.5 mean in contrast to 0.1, which means his experience tell him or inform him one probability is different from the other, right? The other. In other words, he may have his own feeling and experiences, right? Prior experience, which can be replicable, right? Replicable, that identify the probability given for different situations. In our case, success and failure, right? Success and failure. Now, suppose the analyst may predict one success out of 10. We have 10 observation for Y, and he may predict one success. Then she or he would assign probability of 0.1 for probability of Y equal to 1, that is success. However, this does not mean that the analysis presume the existence of a true probability. We say that at the beginning of this chapter, we say there is no true probability because we are giving weight, we are giving value for the future events, right? The future events. So having experience and deciding a certain probability for the event doesn't mean that it is a true probabilities. Just it is a tool for simplifying the specification of probability, right? Probability. The second case is now we don't have an information or we don't have data, or we have small information, small relevant information to our case. So the second case is assume the distribution of Y that we are going to assign probability is a real number or continuous number, right? Continuous number. Now, the way we specify probability will be different from in binary case. In the binary case, we say probability of Y to be 1, success, or probability of Y equal to 0, failure. But here, we do have continuous number, right? We do have continuous number. So in such case, we are going to specify probability for Y, the probability of Y to be less than or equal to Yi. Yi means the observation. It may be 1, 2, 3 or something real number. Or the probability of Y to be greater than Yi. That's the distribution, right? Yi for suitable number yi. Yi means here the distribution, right? The distribution or the prior distribution of y, and we are going to assign for the future distributions. Now, let's assume one often start, or the risk analysis may start with a certain percentage. For example, he may say 90%, and then he specify the value of y, say that the probability of y greater than y equal to 0.9, which means in this case we are assigning random but rational probability based on our prior experiences, right? Prior experience. This to specify the probability distribution, the analyst may consult experts in the subject of the interest, right? In the subject of the interest. But obtaining consult from expert doesn't mean that it is an assessment of probability based on expert elicitation, right? Elicitations. So now here the second approach to assign to judge the probability for y is just based on our experience, prior experience, but we don't have data, right? We don't have data, or we have data, but it's less relevant to our interest, right? To our interest. Now, this is about the second approach, and let's go to the third and the last approach or methods to determine the probability of y, or to measure the uncertainty of y, our performance indicator, Now, this approach requires two bodies, two individuals or bodies. The one is the risk analyst, and the other is the expert in a certain subject, right? The expert in a certain subject. And this approach tries to identify and bring together individuals acknowledged as expert in the subject of concern, right? So determining the uncertainty of y using expert elicitation means just bringing the knowledge of or expertise individuals and let them to determine the probability or to determine or to assign the probability of the uncertain y. Now, when we use expert elicitation is the most important question. So we prefer, as a risk analyst, we prefer expert elicitation when first there is little relevant data, or we have little relevant data that can be available for analysis, right? Or when it is likely that the judgment of the analyst will be subject to scrutiny, right? The first one, we have little relevant data, which is not sufficient enough to deal or to assign probability by the risk analyst. And the second opportunities, or the second way we use this approach is the analyst has already assigned probability, but this probability must deeply scrutinize or deeply analyze, right? Deeply analyze, which means we are not sure, or we are not certain, or we are not comfortable with the probability assigned by the risk analyst, and we need other body to deal with it, right? Other individual, that is the expert, right? That is the expert. In doing expert elicitation, in assigning probability, there are at least three procedures we have to follow. The first one is the analyst here refers the risk analyst should train the expert. You know, both the analyst and the expert has limited knowledge. In fact, the expert has specific knowledge and the analyst has better knowledge than the expert in assigning probabilities for y. So we have to, the risk analyst must train the expert in the assessment of the problem and disseminating among the expert or relevant information and data. So there should be training, and the analyst must provide information to the expert. The second one is the experts are required to formalize and document their rationales, right? They have their own understanding and they obtain some information from the analyst, and then at the second stage, the experts should formalize and document their rationalities to assign or to specify probability distribution, right? Probability distributions. And the third one is the expert should specify their own distribution by determining quantiles, which means once they rationalize and formalize their document, they have to specify probability or the distribution of the parameters or the distribution of the observations by themselves, right? By themselves. Here, sometimes or in practice, we may give weight to the experts to distinguish different expertise. For example, assume we gather 3 experts from different expertise, and they are going to assign probabilities for Y. In such case, right? In such case, we have to give weight according to their expertise. For example, expert A maybe we may give he may obtain, or we may give him higher weight, assume 50%, and the remaining weight for B and C will give 25%. However, in doing or in assigning weight for the expert, there is some argument. The first argument is if we want to give weight for the expert, the first argument we may say we should select high quality expertise in order to give weight, right? In order to give. And the other argues that the expert should be given the opportunity to assign weight by themselves. So there is two views. The first view is if we want to give weight for the expert, we should select at the very beginning, we should select high quality expertise, right? High quality expertise. And the other argued that no, it is not important to give, right? Weight. We should give them the right to assign weight for themselves, which is often practically difficult, right? Practically difficult. The most important thing we have to note here is the analyst is the ultimate responsible, right? Or ultimately responsible for the assessment and obliged to make a final call on the probability distribution. This is the most important thing. If you use formal expert elicitation as a means or a method to assign probability for Y, we should remember that the last responsibility to decide on the distribution and the probability assignment is to the analyst, not to the expert, which means the expert are used an input to set or an input for our decision to set probabilities. This is due to the fact that why analysts give final decision? Because experts have limited but advanced knowledge, or limited or narrow knowledge, limited, narrow, and advanced knowledge on a specific thing than the risk analysts, right? Than the risk analyst. So the other thing is formal expert elicitation is often characterized by its a high costiness, or it is very expensive, right? It is very expensive. So you guys are working in the insurance industry, and if you suggest your immediate manager or immediate boss to use formal elicitation, you have to have adequate justification because it is very expensive to use expert elicitations, right? Expert elicitations. So experts often specify their own probability distribution, but they are not the final decider to say probability for y, right? Y to y. So we can say expert provide the analyst with information for his or her to process and finally transfer probability distribution, right? Probability distribution. Even if you hire experts, the final decision is given for the risk analyst, right? The risk analyst. So this approach has advantage. The expertise can speak their own language and avoid somewhat abstract formalization of using probability. Or in other expression, it may be difficult for the analyst to fully understand the expert's decision if they are just a report of knowledge with no reference to the probability scale, right? The probability scale. Now, the other thing, the most important thing the most difficult thing in formal expert elicitation in deciding uncertainty is building consensus or making rational consensus between the expert or between the analyst. So there are 5 principles which are important to build consensus between the expert and consensus between the expert and the analyst and between the analysts, right? The analyst. So these 5 principles are the first one, reproductivity, right? Reproducibility, which means it must be possible to reproduce all calculation, which means when you use the expert's elicitation, make sure that the method we use should be reproducible, which means used for the next risk assessment, right? The next risk assessment. The second principle is accountability, which means the base for probabilities assigned must be identified. What was the base to assign probability? Was it wrong? Was it right? It should be accountable, right? It should be accountable, the method or the basis we use to assign probabilities. The third one is empirical control, which means the method we assign probability must be susceptible to empirical control, which means it should be implementable, right? Empirical control means it should be feasible when we apply it, right? Or it should be supposed for empirical investigation, right? Empirical investigation. The fourth one is there must be neutrality. The fourth principle to build consensus between the parties involved in risk analysis is neutrality. So the method for combining or evaluating expert opinion should be encourage experts to state their true opinion. Neutrality, which means their decision to assign probability should not be, right? Should not be affected by other interests. It should be a result of their own expertise knowledge, expertise view, right? The fifth one is fairness, which means we already say, assume we have 4 experts, and those 4 experts should be treated equally in the process of assigning probabilities, right? In the process of assigning probabilities. So this is all about how to assign probability for y, right? Probability for y. We often refer y as measure of performance, or we can say the left-hand side of the model, econometrics model, right? Economics model. Now let's go to the application of Bayesian approach in risk analysis. If you remember that in chapter 3, we try to distinguish the two main or area of risk analysis, that is approach, the classical and the Bayesian approach. In fact, most of the analysis we used in this course and in the practical application is about the classical approach. But there is a situation where Bayesian approach is important in risk analysis, right? In risk analysis. So we only take maybe one example to see how the Bayesian statistics is used in risk analysis, right? Used in risk analysis. Now, let us start our discussion by reminding what Bayesian statistics consider. So, Bayesian approach give a unified approach to simplification of probability of y greater than or equal to the observed y. The observed y. Y means here the parameter or sample. We can say sample parameters, right? It may be mean value, it may be overall distribution, or it may be standard deviations, right? It is up to our assumption in risk analysis. Now, this approach, or in order to apply Bayesian approach in risk analysis, there are some common procedures we have to follow, right? Common procedures. The first thing is we have to introduce the parameter. First thing, we have to introduce the parameter which represent the state of nature. And the way we specify probabilities is given in this equation. See here, probability of y greater than the probability y to b, right? Y to b, maybe 1 or 3 or some real number equal to the interior of y greater than less than or equal to y. This is in case where the parameter and h represent prior distribution. If you remember that Bayesian approach is based on prior distribution, right? Prior distributions. And this figure, probability of y greater than theta, is normally given by a common parametric distribution. In statistics, there are different distributions, right? There are different distribution functions, maybe exponential, log, sub-exponential, different types of distribution function. So the specification or the determination of the distribution of our parameter is up to the nature of the data or up to the assumption of the risk analyst. So Bayes' theorem tells us how to update prior distribution. Now here you have to remember that we have prior distribution and we are going to update it, or we are going to determine posterior distribution using new data, right? Using new data. We have prior distribution, we obtain new evidence or new data, and we are going to specify future or posterior distribution, right? Posterior distributions. Now, let's see how we can implement, right, or use Bayesian approach in one of the most types of risk, the so-called health risk. Now, we are going to use Bayesian approach to specify probabilities or to use for risk analysis, right? Now, we only take health risk. We can consider different types of production risk, cost risk, and other types of risk. For this purpose, I select only health risk. So let's see the application of Bayesian approach in determining health risk. We should start from the assumption. Suppose we test a patient when there are indications that the patient has a blood disease, right? It has a blood disease. Let x be 1 or 0. 1 or 0, the value of x, according to whether the test gives positive. If it is a test positive, we assign 1. Or if the test result give negative, we will give value 0 for x. Furthermore, let the parameter be the true condition of the patient. We often assume the parameter is the state of nature, which is real, right? Which takes from prior experience, right? Which takes from prior experience. Now we assume the parameter, we have true condition of the patient, indicating the true condition of the patient or the state of nature, which is defined as, which means parameter equal to 2 if the patient is seriously ill, and the parameter equal to 1 if the patient is moderately ill, and parameter equal to 0 if the patient is not ill at all. So we have 3 values of the parameter: 2 for serious ill, 1 for moderately ill, and 0 if the patient has not totally ill, not ill at all. Now, from general health statistics, this is general knowledge. We often consider the existing knowledge to assign probabilities. From general health statistics, suppose that 2% of relevant population is seriously ill. 2% of the population is seriously ill. 10% moderately ill, and 88% is not ill about from this disease, the blood disease. Now, let's see how to approach this one. Remember 3 points here. The first one, the result we are going to test. X to be 1 or 0. 1 positive, 0 negative, tested positive or negative. And the other one is the value of parameter, 2 for seriously patient, 1 for moderately, and 0 not patient or not ill. And from general information, 2% of the population, we don't know the population. The population is unknown. We say 2% will seriously ill by this disease, blood disease. 10% moderately ill, and 88% not ill. Now let's see the application, right? Let's see the application. First, from this health statistics and without using additional information about the patient, we can specify prior distribution. Our prior distribution, the probability of parameter to be 2 is 0.02, which means 2%, and the probability of parameter to be 1 is 10%, which means 10%, and the parameter without any information is available information, and the probability of parameter equal to 0 is 0.88, that is 88%. This is the information what we have without any references, right? Secondly, let us consider additional information. Second, suppose we know from experience that the test will give positive response. The test will give positive response, which means X is equal to 1 in 90% of the case if it is being applied on patient that is seriously ill. Now, we refer our experience. And our experience tells that the patient be positive or the value of X is equal to 1 will be 98% if it is seriously ill, 60% if it is moderately ill, and 10% if the patient is not ill, right? Not ill. So we specify probabilities based on our experience. Thus, conditional probability, we have true probability already here, true probabilities here, and the conditional probabilities can be formulated as follows. Probability of X to be 1 under the condition when the parameter equal to 2, that means seriously ill, is 0.90, which means this figure. The probability of X is equal to 1 under the condition the patient moderately ill, 0.60, and probability of X is equal to 1 under situation that no ill, that is 0.1, right? So we refer this in statistics likelihood function. It is likelihood functions, which is conditional probability, right? conditional probability. The third step is we have to combine both probabilities, right? Both probabilities, that is prior distribution and our conditional distributions, so as to compute posterior distribution or posterior probabilities, which means the future probability. That is probability of the person to be ill under the condition where, or to give positive response or positive test. That is the probability the patient is seriously ill, given that the test give a positive response. So simple probability calculus will give us probability of X to be 1, that is the test to be 1 positive, equal to probability of X test to be equal to 1 in the condition or in situation where the person is seriously ill, 2 times probability of this figure plus probability of X is equal to 1 when in the condition where the patient is moderately ill, times probability of theta or probability of the parameter equal to 1 plus probability of X equal to 1 in a situation where no ill, right? No ill, which means simply 0.9, that is the probability of X to be equal to 1 when the person is seriously ill, times, this is, you remember 0.02, this is population distribution, the overall population distribution to be ill, to be seriously ill, 0.9 times 0.02 plus 0.6. This is the conditional probability when the person is moderately ill, times 0.10. We already assigned this figure at the very beginning from the population, plus 0.10 times 0.88. We will get 0.166 or 16.6% of there is chance to be seriously ill, or those or we can say the 16.6% to have positive test, X is equal to 1, or we can say about 83.4 is have a probability to be negative test result, right? Negative test result. Now, using Bayes theorem, this is Bayesian formula. The Bayesian formula we already seen in the last session. Now we are going to test the probability of the person that is seriously ill to have a positive test result. This is, you can say, probability of parameter equal to 2 under the condition the result of test is to be 1 positive, equal to, we can use this formula, which means 0.9 we assign for seriously ill person to have positive response based on our experience, times this is overall population's test result to have blood test be positive, divided by 0.16. This is the overall probability of a population to be, which means this figure, right? This figure, right? This figure, you can see here. That is the overall probability of the test to be positive, right? So we'll get 0.11. That means if the person is seriously ill, he has a probability of tested positive, or 11%, or 0.1 probability to be tested positive. Wow. So this figure, compared to 90% we expect, is too low, right? It's too low. So in this case, the doctor must be cautious, or must be considered, or must be cautious in communicating the patient. ለምንድነው ከሆነ ሪዛልታችን 0.1 መጣው፣ ግን throughout overall experience የሚያሳየው 90% ወይም ደግሞ probability to be positive seriously ill ከሆነ 90% አካባቢ ነው ወይም 0.9። ነገር ግን our assumption 0.1 ነው ያመጣው። ስለዚህ the person must be cautious in communicating the patient, right? And thus, the doctor must solve or as a risk analysis, we should consider other means to increase the probability of the patient, the probability of most or seriously person to have positive tests or test result. Now let's go to the fourth step. Why we go to the fourth step? Because our prediction is less than our experience. 0.11 is very less than 0.9. That is our experience step. So we go for the next step. The situation can be improved by performing additional tests to provide more information, right? So let's go to additional test. Now, the most common additional test in such condition is to make two tests. Test A, test B. Like, for example, you may see that for doping case, doping case, those who guys or athletes, they usually have tests, doping tests. And the agency doesn't trust one test. He may distribute their sample for different hospitals or for different tests. And the decision is if all tests indicate positive doping, right? ስለዚህ በዛ ላይ ኬዝ እናየዋለን። ለምሳሌ ዶፒንግ ኬዝ ካለ ዶፒንግ አንድ ቦታ ላይ ብቻ ቴስት አድርጎ የከለ ሰው ዶፒንግ ችግር ተገኝቶበታል አይደለም። They distribute their samples for different tests. Test A, test B, test C, like that. And all the tests should provide the same result, right? The same result. Now let us consider our case, right? Our case here. For instance, we can compute the probability of the patient to be seriously ill, given that both tests, test A and test B, have shown a positive response. So we broaden our case. Let now give values. Let xi be 0 or 1. This is 1 means to be positive or 0 is negative. Xi represented by 2. I 1 and 2. I represent 1 and 2. That means for test 1 and test 2, or observation 1, observation 2 for test A and B respectively, right? Respectively. Now, the sought probability, the probability we are looking for, can be then write as probability of the patient seriously ill under the condition where x1 equal to 1 and x2 equal to 1. Both, so we are going to test the probability a person seriously ill under the condition where test A give positive result and test B give positive result. X1 and X2 refers the value of A and B respectively. Considering the first situation after the first test has been performed, because first we have to test A, then we have to go for test B, right? Test B. Now, instead of using uncertainty distribution of the parameter, that is 2, 1, and 0, based on the health statistics, we now start with updating probabilities, right? Updating probability, which means we are determining posterior distribution, probability of the person seriously ill under the condition where both tests provide positive result. And probability, ለእያንዳንዱ assignment እናደርጋለን probability based on the information that the first test showed as a first respond. ይሄ እንደቀድሞ አሁን 90 60 10 አይደለም እናስቀምጠው። እዚህ ኬስ በስቴፕ 3 ላይ የራሳችን probability አግኝተናል. For example, probability of the person that is seriously ill to be positive is 0.1. ይሄን አግኝተናል። ስለዚህ ማን ይቀራል? Probability of the person moderately ill to have positive response and probability of the person not ill to have positive response. እያንዳንዱን ይሄን እናገኛለን ማለት ነው። ስለዚህ በዚህ ኮምፒቴሽን ተመሳሳይ ኮምፒቴሽን ነው ቅድም ከሰራንበት ጋር ነው 0.36 for probability of moderately ill patient to have positive blood test. We get this competition, the same competition with the prior one, 0.36. And probability of the person who is not ill to have positive blood test is 53. When we sum up the three, 0.11 plus 0.66, 0.36 plus 0.53, it must be equal 1 because 1 is the maximum probability, right? The maximum probabilities. Now, the tests are conditionally independent in this sense. Tests means test A and test B. We assume they are conditionally independent. That the probability the second test gives a positive response, given that the patient is seriously ill or moderately ill or not ill, does not depend on the result of the first test. This is important concept. So we assume there is independent conditional probability distribution, right? Probability distributions. Thus, we can show the probability distribution as follows. Now, probability of X2 test 2 to have or to provide positive output when the patient is seriously ill under the condition test A, test 1 equal provide positive response will give us probability of X2, that means test 2 to provide positive response under the condition where the patient seriously ill, we get 0.09. ስለዚህ ለሁሉም ዲስትሪቢዩሽን ይሄ መጀመሪያ የምታስታውስ ከሆነ ይሄ ዲስትሪቢዩሽን አለ 0.90 0.60 0.1. This is seriously ill, this is moderately ill, and this one is no ill. So this is independent distribution for both tests, right? For both tests. This means we are assigning similar probability used for the calculation of the probability a person seriously ill to get positive blood test, right? Blood disease, right? Test for blood disease, right? Blood disease. So we can use this formula, that is the Bayesian formula, right? The Bayesian formula. So we get 0.9, a distribution of seriously ill, times 0.1. This is the probability we compute on the third step and divide by total probabilities, right? Total probabilities for all cases. We get 0.27, right? We get. So this posterior probability is much better than 0.1. We assume 90%. And the third step, we get 0.11. And at this step, after we consider test A and test B, we get 0.27, which means both test A and test B commonly provide a 20% chance, right? A 27% chance that a person who is seriously ill to have positive blood disease test, right? Blood disease test, which is greater than 0.11, right? 0.11. And the last step is the fifth step. We would like to go one more step because still 0.27 probability compared to the population distribution of 0.90 is lower. So we have to go one further step, right? One further step. What is that further step? This step is to include specific information. Let us add specific information that the doctor has about the condition of the patient, right? The condition of the patient. Now we have patient, we are going to obtain additional information about the condition of him or her. Well, suppose that the patient has shown some rather strong symptom of being seriously ill. Now he's going to be seriously ill. Symptom አሳይቷል. Serious ill የመሆን ማለት ነው. Well, now the doctor finds that the above probability distribution is not reflecting his view, which means 0.11 and 0.7 is not reflecting his condition. So concerning the state of the patient, given the present state of knowledge, balan, understanding or experience. So instead, the doctor assign the following probabilities expressing his uncertainty about the parameter, right? About the parameter. So he just take modification. So, probability of the patient who is seriously ill was what? 0.02 number. ስለዚህ ምን አደረገው? ፖዚቲቭ ሪስፖንስ ለሞመንት ነው ከ0.02 ወደ 0.04 ከፍ አደረገው because he shows strong symptoms to be ill. And probability of moderately ill person to have positive blood test result, it was 0.1. Now he increased about 0.4. And the probability of a person who's not ill to get blood test result positive, that is for blood disease, it was 0.88, and now he reduced 0.2. And the sum of all probability must not greater than 1. It should be perfectly 1. 0.4, 0.4, 0.8 plus is 20. 0.2 will be 1, right? Will be 1. Now you can follow similar procedures, step 2, 3, and 4 to compute the probability, right? You can follow. Now this I give you as a homework to complete this step. ቅድም ያለፍናቸውን step 2, step 3 እና step 4 just repeat it using this formula. እዚህ ጋር 0.02 ያልነው በ0.04 መተካት ነው። 0.01 ያልነውን በ0.4 መተካት ነው። 0.88 ያልነውን በ0.2 መተካት ነው። All the process is the same. In order to check the value, you can check the value. The overall probability for a person who is seriously ill to be or to have positive blood test is 58%. Right? 58%. And combined result, ይሄ በ0.11 መልክ ያገኘው ነው። ሁለቱ ደግሞ ቴስት ኤ እና ቴስት ቢ ደግሞ 0.69 ይሰጣሉ። You can check at your home. Just follow the same procedure, right? Just follow the same procedure. እያዳመጣችሁ ነው? እያዳመጣችሁ ነው? ድምጻችሁ ጥፍት ብሏል። ምንድነው? ድምጻችሁ ጥፍት ብሏል። አቶ ድሪባ
እያዳመን ነው። አቤት እያዳመን ነው።
So ይህንን at home you can መልሱ 0.58 ነው እና 0.68 ነው። ይሄኛው ኢንዲፔንደንት ቴስት እናደርግ ነው። ቴስት 1 አንድ ቴስት ብቻ ስናደርግ 58 0.58 ነው የሚኖረው, which means ፖዚቲቭ ብለድ ቴስት ለማግኘት አንድ ዘ ሲናሪዮ። ይሄ ደግሞ ቴስት ኤ and ቴስት ቢ ስናደርግ ሁለት ቴስት ስናደርግ always greater than this one. ይሄን ክሮስ ቼክ አድርጉ። the same procedure ነው, just ቁጥሩን ብቻ መቀየር ነው, right? Same procedure. So now I'm going to go another issues we have to discuss. So let's go to how to specify prior distribution.
Hello, doctor.
አቤት አትድሪባ።
አሁን እዚህ ጋር አሁን ቅድም ያየነው ነገር አለ እና አሁን እዚህ ጋር ምን አደረገው? ያኛውን ቅድም የነበረውን ዲስትሪቢዩሽኑን ራሱ ዲስትሪቢዩት ሲያደርገው በእንትን ነው መጣ ነው ጀስት ዲስክሪት ዲስትሪቢዩሽን ነው እየተጠቀምን የመጣ ነው የነበረው። ዲስክሪት ዲስትሪቢዩሽን ተጠቅመን መጣንና አዘላስት እነዚህን ቴስት እያደረግን መጣን። አሁን ግን ይሄንን ሰሙን ለምን in case of discrete distribution normally probability value sum እያደረገ ነው መጣ። እዚህ ጋር ደግሞ አሁን ቅድም ያየነው የፕሮባቢሊቲ ቫልዩን ኢንተግሬት ሊያደርገው ነው። አሁን ያለው ነገር ዲኤች ቅድምም አይተን ነበር ከላይ ፒሪዮድ ዲስትሪቢሽኑን እሱ ፋንክሽን ቅድምም አይተን ነበር፣ ግን እዛኛው ላይ አልተጠቀምንበትም። ኤል ቴታንም አልተጠቀምንም። ቅድም ነበር ኤል ቴታ ላይክሊሁዱ ነው እና ሁለቱ ነገሮች ትንሽ ግልጽ አይደሉም ለኔ ልዩነታቸው።
Let me go back and see what your question. ከተረዳው ወደ ልመለስና እንትን ልበል። እዚህኛው ላይ ይሄ እዚህ ጋር የተማርነው ከቅድም ካየነው ከባይናሪ ዲስትሪቢዩሽን ይለያል። ይሄ አሳምፕሽን የወሰድ ነው ራይት። አንተ ያለው እዚህኛው ጋር ነው አይደል?
መጀመሪያ ላይ ያየነው አሁን ደግሞ ተመልሰን ወደ እሱ
ይሄ ጋር ይሄ ነው። ይሄኛው ዲስትሪቢዩሽን ኦፍ ዋይን ወይም ደግሞ የአንሰርቴኒቲ ኦፍ አባውት ዋይን ዲተርሚን የምናደርግበት ነው ይሄኛው አፕሮች። ምናልባት እንዳይቀላቀሉ ነው ታይትሉ ይለያያል። ይሄኛው how to assign probability for y ነው right under the condition binary case ያለን continuous case ሲሆን ደግሞ ይሄ አለ። እዚህኛው ላይ ግን ስንመጣ ምንድነው ይሄ Bayesian approach ኢምፕሊመንት ማድረግ ነው right። ይሄኛው ሌላ ታይትሉም እንትን ኬዙም ይለያያል። እና ባካል ተከታተልከኝ መሀል ላይ ወጥተ ነበር ለዛ ነው እዚህ ጋር ይሄኛው application of Bayesian approach in risk analysis which is different from competition of or assigning probability for y የሚለይ ነው። ሴናሪዮ ግን in case ሴናሪዮ ማካስፈለገ distribution of y is not binary in this case binary አይደለም because we give 2 1 and 0 right random number no right or rational or real number no ተጓተና የተለያዩ ኬዞች ናቸው።
ስለተደባለቁብኝ ነው
መሀል ላይ ወጥተ ነበር መሀል ላይ ለዛ all right so now let's see specifying prior distribution። ይሄ ደግሞ ቀድሞ የነበረው ዲስትሪቢዩሽን እንዴት አድርገን ስፔሲፋይ እናደርግ ነው ያለን ዲስትሪቢዩሽን something distribution አለ ማለት it's not a guarantee for or posterior distributions። ስለዚህ prior distribution እንዴት ስፔሲፋይ እናደርግ ነው የትኛውን ዲስትሪቢዩሽን እንጠቀም ነው different distributions። Now let's start from fundamental equation of Bayesian analysis right. We use Bayesian analysis here. So this is a probability distribution for ይሄ ምንም አይደለም just probability distribution under Bayesian approach በዚህ አገላለጽ ነው የሚሰጠው ነው። So this is just an integer right integer probability of y greater than or equal to y observable. This is observable ነው whether true or to be one or to be some figure ቀደም እንዳየ ነው ሁለት ሊሆን ይችላል አንዱ ይችላል ዘውና አይታወቅም። So assumption ነው ይሄ distribution በባይጂያን ዲስትሪቢዩሽን ወይም ደግሞ በባይጂያን approach probability distribution የምናይበት approach ነው። It's not something የሆነ የተለየ ነገር አይደለም right. So we always start from prior distribution for the parameterችን አለን የዛ distribution is already known right. We must have parameter actually parameter ከሌለን ወዴት መንቀሳቀስ አንችልም። So now from Bayesian standing point of view ከባይጂያን መነሳት prior distribution should reflect what the knowledge possessed before the relevant data are at hand. Assumption ይሄ Bayesian approach we just specify probabilities based on prior distribution and this prior distribution can be validated by having real data relevant data validate መደረግ ይችላል። However in practice the specification of prior is often difficult and certain class of techniques should have to be used right have to be used a distribution አለ distribution prior distribution ይገጻል ለማግኘት እንችላለን። So let's see what techniques we have to use in order to specify prior distribution. We are not talking about posterior, we are talking about prior distribution which is a basis to determine posterior distribution right posterior distribution. So the first technique is the so-called non-informative prior distribution. Non-informative prior distribution. This technique is based on the idea that the distribution reflecting or the distribution the distribution reflect total lack of information about the parameter. ለዚህ ይሄኛው ምንድነው non-informative ነው. So we do have lack of information about prior distribution. And this, we cannot specify the prior distribution due to lack of data. Right? For example, in binomial case, a non-informative prior distribution for parameter P, let's assume parameter P is then given by uniform distribution on the interval between 0 and 1 because it is binomial, right? It's binomial distribution, right? Binomial distribution. Now, non-informative means prior distribution is not reflecting the actual distribution because we do have limited information or we are suffering lack of information. Wait, now the question is, what about the situation where the parameter takes a value on 0 and positive infinity? Okay, the binomial distribution randomly ማስቀመጥ እንችላለን non informative ነው ምክንያቱም ኦብዘርቬሽናችን 0 and 1 ነው likelihood ወይም ደግሞ probability to be 1 or probability to be 0 ነው ስለዚህ ይሄ ኢንፎርማቲቭ ባይሆን ዲስትሪቢዩት ማድረግ እንችላለን ነገር ግን if we have parameters which have with positive infinity 0 and it is unknown, right? Should we use a so-called improper prior having a density equal to 1? Density means the summation of all prior distribution having limited observed data to be 1. Here in the way, when it means density function, it means the sum of probabilities for the limited observations. The question is no. We should not use density or improper prior distribution to predict posterior distributions. So such distribution should be avoided. Positive infinity should be avoided. And then even when the non-informative distribution is proper, we should avoid it. Which means improper prior distribution based on the density function. Density means overall probability equal to 1 በሚል ማለት ነው for unknown number. ይሄ መጠቀም የለብንም ነው. So the most practical case, the analyst should have some knowledge. And that information should be incorporated to give a proper informative probability distribution. Right? So this is important thing. We should have knowledge, and that knowledge should be incorporated in the analysis so as to have informative, proper probability distributions. Now consider the Poisson distributions. Actually, distributions ብዙ statistics ሆኑ ብዙ ነገር ማለት አልፈልግም። በጣም ብዙ አይነት distribution ያለው functional distribution, Poisson distribution, and the problem of specifying a proper distribution for here. Assume this is which is lambda, but referring the parameter, right? We could ignore the value of the parameter that are very large. Why we exclude very large parameter? Very large parameter for positive infinity ካለ very large observation avoid እናደርጋለን parameter. Why? It may cause outlier effect. Outlier effect ሊያመጣብን ስለሚችል we should have to remove it, right? So why should we then use priors that give positive weight to such values? ለምን እንጠቀማለን? outlier-ዎችን avoid ካደረግን ለምንድን ነው prior values positive values የምንጠቀመው ነው? So the question is because it probably the choice of non-informative prior is more motivated from the need of having objective prior rather than reflecting total lack of knowledge. ዓላማችን lack of knowledge solve ለማድረግ ሳይሆን we want to have objective prior, objective, not subjective prior. So non-informative distribution may be a simple way of establishing consciousness, but it could mean ignoring significant information, right? Significant information. This is about the first approach, non-informative approach. The second approach is using conjugate distribution. Conjugate distribution. We are evaluating or specifying prior distribution using conjugate distributions. Conjugate distribution means we have different prior distribution, two different prior distributions, and some of this prior distribution can be conjugate together, right? Which means the prior and posterior distribution belong to what? The same distribution class. ከዚህ በፊት የነበረውና በቀጣይ ዲስት እናደርገው ምንላቸው the same distribution class ሊመጡ ይችላሉ። For example, Bayesian distribution and gamma distribution, they can be a same group. Different distribution ናቸው ነገር ግን በአንድ ግሩፕ ውስጥ ሊገቡ ይችላሉ ማለት ነው። Right? በአንድ ግሩፕ ውስጥ ሊገቡ ይችላሉ ማለት ነው። So this is conjugate distribution in order to specify prior distribution. Perfectly aligned የሚያደርግ prior distribution ማግኘት ካልቻል we can take distribution that have similar natures. That can be one group. As it is presented, Bayesian distribution can be joined or conjugate with gamma distribution, right? Gamma distribution. The third and the last approach to specify prior distribution is the maximum entropy prior. Maximum entropy prior, right? It is an interesting approach for specifying prior distributions. Interesting approach. This approach means a specification of some of the feature of distributions. Some of the feature of distributions. Some, not all. For example, we will see the distribution of mean, average value, or the distribution of variance. Not all. Maximum entropy prior means we don't have, or we cannot test all distributions. We are going to test only the distribution of some specific items. The distribution of mean values, or the distribution of variance, or the distribution of covariances, right? Right? In the math and challenge, so as to determine prior distribution. Well, so that is the three approaches to specify the prior distributions. Now, let's go to how to assign or assess uncertainty for vector x. Explained variable, the variables in the right-hand side in the model, or factors that explain our risk measures, right? Risk measures. Now, in order to assess uncertainties about the vector x, we are going to use one example. We have already discussed about it in chapters. That is cost risk, right? That is cost risk. So just you can refer our problem in chapter 3, and we develop the model. Total value of y equal to summation of I1, that's k for real number, and xi is the factor that affect y. Summation of x. Maybe cost factors, right? Cost factors, different cost factors. Y represent investment cost, and xi represent cost element, the factor that affect the cost. If we judge the cost of the element to be independent, x1, x2, x3 is independent each other, we can use a procedure of previous sections to assess uncertainty and specify probability distribution for x1, xi. However, in practice, x1 may not be independent from x2, x2 may not be independent from x3. So this is the most common problem in finance studies. Finance ላይ በጣም common study ነው። ምክንያቱም the independent variable may not be independent each other, right? Each other. For example, assume the cost elements are all strongly influenced by oil price. ብዙ ኮስቶች አሉ፣ ብዙ አይተሞች አሉ ኮስቱን አፌክት የሚያደርጉ ነገር ግን ኦይል ፕራይስ ሌሎችን አፌክት ያደርጋል። Assumption, which means oil price may be x1. It affects x1, x2, x3. It should not be in the model. Now the question is how to incorporate this in the assessment. Probability assessment ነው. So the first approach is we have to remodel. Remodel means change this model, this distribution, right? This distribution, because there is multi-correlative problem between the cost factors. Now, how do we do remodeling? Let's see an example. Let x be the value of underlying factor. Underlying factor, for example, oil price, which affect other cost elements, x2, x3, x4. Based on latent regression, just avoid the term latent. Based on regression, we write what? We write xi to be x2, x, which means xi affected by x to show the dependency of x. Dependent nature. ሌሎች ኤክሶች በኤክስ ኤክስአይዎች በኤክስ ዲፔንደንት ናቸው። To give xን ኮምፒት ለማድረግ x means here is oil price. We change the cost element to be independent. Yep, that's true. The other cost element must be independent. x1 ሌሎቹን x2 x3 affect የሚያደርግ ከሆነ we have to assume x2 is independent of x3, x3 is independent of x4 መሆን አለበት. By specifying an uncertainty distribution of x and of xi given x, we can compute the uncertainty distribution of y as follows. Right? Compute the distribution of y. In fact, which is not our case. We are dealing about vector x. Now we draw a number of x. A number x. We draw x. Just pick x among different x from distribution of x. ይሄ x oil price አለ እሱ ምን አለው ኦብዘርቬሽን አለው year 1 year 2 different observation አለው just we pick one observation and then use this as a starting point for drawing the value of xi የሆነ value draw ካደረግን ወይም ደግሞ የሆነ observation draw ካደረግን we cannot specify the distribution function between vectors vector x. This data are then used to produce y value. ስለዚህ value of x ካወቅን ነው we can produce the value of y. x ባልታወቀበት we cannot compute the total cost. Right? The same procedure is repeated until we obtain the resulting probability distribution of y. Now, and then y determine የሚያደርጉ deeply we have to go deeply until we find the distribution of y. ምሳሌ 5 x ፋክተሮች ካሉ ኮስት ፋክተሮች ካሉ ሶስቱን ብቻ ወስደን probability distribution determine ማድረግ አንችልም. We have to rigorously go. Now the challenge is to find a simple way of expressing judged independence. ትልቁ ችግር ይሄ ነው. We say that x1 affect other x's by other cost factors x2 x3. But we still assume that x2 is independent of x3, x4, and like that. That is a very difficult judgment, right? So now, where xi related to quantity of xi, that is x2, x3, x is oil price. We may go to one step forward to express the xi by the equations. Let's see, independence of xi, independent of x, depend on x እንደሆነ ለመግለጽ we can use this distribution. This is a coefficient and this is a constant and x prime I. This x prime is just the unknown values, the undetermined number of x factors, right? X factors. Where the observable quantity x and x are judged independent and xi has distribution of f. Of course, we have to know the distribution of x. X in distribution is normal, exponential, log distribution ካልታወቀ relationship determine ማድረግ አንችልም. We have to know the distribution of our our cost factors. So for example, we can only take the mean values or the variance. ቀደም እንዳየነው maximum entropy approach የተጠቀመው ነው mean ወይም variance መውሰድ እንችላለን ወይም ደግሞ ካለን ሁሉንም observation መጠቀም እንችላለን. Right? So the basis for using this equation is regression analysis. ALHP የሚሰራው y in terms of regression model ካልተገለጸ we cannot apply this relationship between the independent factors. So now why we express this equation? We express this equation because we want to plot the distributions. Plot ማድረግ እንፈልጋለን. Observationዎችን plot ማድረግ እንችላለን. x1 x2 ይሄ observation አለ ብለን we want to determine that. Right? We want to determine that. Now we have two formulas. You remember here, this is the main model and this is the equation used to adjust x1 affect other factors. Now we can rewrite this model. We can rewrite this model by incorporating this arrangement. So we can say y equal to summation of a plus x plus summation of beta, the constants, plus summation of xi, other xi, right? ቀጥታ በዛ ሞዴል ላይ ይሄኛውን ኢኩዌሽን ያስገባ ነው። ሳይሜሽን የተጠቀመው ምንድነው? We don't know the number of x's. The number of x may be more than one, right? So this distribution can be tested by regression models, different estimations. For example, ይሄንን estimate ማድረግ we can compute, we can do simulation analysis in order to know the distribution of x and the distribution of y, right? Distribution of y. This is remodeling is one part to assess uncertainty of x. The other way of incorporating dependency of x1 or x2, x3 by x1, we can use correlation analysis or correlation coefficients. It is represented by this one. This is correlation coefficient between x1, xi, and xj. ሌላው አንዱ ከአንዱ ዲፔንደንት ነው ወይ መሆኑን ለማወቅ ኮስት ፋክተሮች አሉን x1 x2 x3 ያላቸው አሉ አንዱ በአንዱ አፌክት መደረግ መሆኑን ለማወቅ ምንድነው we have to use correlation coefficient. I think you know what correlation means. Correlation of x1 with correlation of x2, right? And others. We can say xj. I represent 1 to 3, j represent 1 to 3. We can say just compute the correlation coefficient, right? So to interpret this coefficient, we consider our uncertainty distribution of the pairs, uncertainty distribution of x. In coefficient በማየት we can interpret the distribution of xi, xj here and here distributions. From these distributions, various summarizing measures can be derived. In correlation distribution በማየት correlation as an indicator of distribution of x. Then, based on this, we can derive different measures, including correlation coefficients. How we can compute correlation coefficient? We can use this formula. Correlation coefficient equal to summation of, or the sum of, E represents sum of, xi represents this one, minus ui represents the mean value, times xj, the observation one, this one, minus the mean value times or divided by standard error of xi, standard deviation of xi and standard deviation of xj. And በመጠቀም correlation compute ማድረግ, which is an easy formula, right? It's an easy formula. Now, once we compute the distributions of the correlation coefficients, we can also determine other parameters, the mean, standard deviation, and the coefficient, right? We have the coefficient. Based on these values, we can determine or we can calculate the distributions. For example, the distribution of y in terms of mean can be calculated by what? Summation of, this is the mean value of x1, x2, x3 like that. Mean value of x1 plus mean value of x2 plus mean value of x3, we will get what? The mean value of y, so that we can know the distribution of y, right? The distribution of y. In fact, we assume here y and x are normally distributed, right? Normally distributed. The same time, we can also measure the variance of y, right? The variance of y, the dependent variable. Based on the figure, you can use this formula, right? That is dimension of the standard deviation, or the standard deviations of, or the variance of I square plus 2 times summation of, we can say here the coefficient of ij times the variance, the standard deviation of I and standard deviation of j. Right? We can compute, use this formula, right? This formula. Well, this is how to determine the assessment, or how to assess uncertainty of vector x. In fact, when you determine uncertainty of x, we can by default determine uncertainty of y. Having the value of x means we can easily determine the value of y. Of course, this example is based on the given numbers. The numbers are mean, variance, and the correlation coefficients, right? Correlation coefficient. Now, the last important section of this chapter is reliability analysis. Do you have question, guys? Sorry. Do you have question?
Doctor, is there any software can provide such kinds of calculation, or it's done always manually?
Of course, there are different types of softwares. ይሄንን ያየነው በሞዴል ኬዝ ነው ራይት ሞዴሎች ናቸው አሁን ሞዴል y ኮስት ነው ኮስት ፋክተር x1 x2 ያለ ይሰራ ነው አይደል ይሄንን ዳታው ከተገኘ የኤክስ ቫልዩ ከተገኘ ኦብዘርቬሽን ማለት ነው ምናወራው በኦብዘርቬሽን ነው ኦሬዲ ሞዴል ሲወራ ኦብዘርቬሽን መኖር አለበት
ልክ ነው
ስለዚህ ሞዴል ማንኛውም ሶፍትዌሮች ይሰሩታል ለምሳሌ ስካታ ይሰራዋል ኤስፒኤስኤስ ይሰራዋል ኢቪዩስ ይሰራዋል ብዙ ሶፍትዌሮች አለ ይሄን ኮንክሉድ እናደርጋለን ምክንያቱም our observation may be too many sorry በጣም ለምሳሌ 100,000 ኦብዘርቬሽን ካለ the value of x1 x2 አጠቃላይ ኦብዘርቬሽን 100,000 ቢሆን ማኑዋሊ አንሰራውም ይሄንን right ማኑዋሊ ስለማንሰራው በኮምፒውተር ይሄን ኦርደር ስናደርገው is very easily by the way ቁጥሮቹ እዚህ በሳይሜንሽን ምናምን በኢንቲጀርስ የቀመጡ አስቸጋሪ ይመስላሉ በሶፍትዌር ግን በምናስገባበት ሰዓት is very simple just compute y compute the standard the mean values is very easy to compute right even ሌላው ይቀርና ኤክሴል ይሰራዋል right ኤክሴል ይሰራዋል right just እያሳያለ ፕሮሲጀሩን አድቫንስ ኮርስ ስለሆነ አንዳንድ ተርሚኖሎጂዎች ለምሳሌ እነዚህ ሚን ቫልዩ ስታንዳርድ ዲቪዬሽን ኮሬሌሽን ኮኤፊሺየንት እነዚህ ቴክኒካሊ የምትማሩት ስታቲስቲክስ ላይ ነው right ያው አንደር ግራጁዌትም ስትማሩ ማስተርስ ላይ ደግሞ ምናልባት ሪሰርች ሜትድ ከተማራችሁ እዛ ጋር የተወሰነ ፓርት ይኖረው ይችላል common knowledge ነው ዲቴል መሄድ ማልችለው I cannot do all of the things here right
thank you
all right so I think we have only 30 minutes and we have about 20 slides I have to no less than 20 slides so the other question is how we can measure reliability analysis now you are a risk analyst you have your own understanding or your prior experience and you may have actual data historical data now the question is before we make risk analysis we have to take the validity test right validity test እዚህ ጋር ቁጥሮችን ሳይሆን ቫሊድ የምናደርገው ፕሮባቢሊቲ አሳይመንቶችን ነው let's see reliability analysis now generally there are two types of reliability analysis the first one is traditional reliability analysis and the other one is structural reliability analysis so today we will see what does mean traditional reliability analysis and how we can apply it and how we can make structural means it is based on a model expression in terms of models you know structural so we will see it so now let me start from traditional reliability analysis right traditionals so we have to start the application of traditional reliability analysis based on some given points or given information so let us consider a parallel system of two components parallel and two components and let's assume we express the model as follow which is monotonic structure right monotonic Baelijan right Baelijan so we have the model assume this is the model just we represent this one the component and this is the model assumption ነው ከየት የሚመጣ ቁጥር አይደለም we have two components and we express the relation between this component in terms of model that is monotonic structure right so just a model represent this one ይሄንን በy መግለጽ ይችላልላችሁ ቅድም ባየነው y በሚል ማስቀመጥ ይቻላል it's just different types different representation equal to this is x this is the model equal to 1 minus 1 into x1 times 1 minus x2 because we do have two component 1 x1 component 2 x2 ይሄ ሞዴል ኤክስፕሬሽን ነው ከዚህ ሞዴል ተነስተን ሪላያቢሊቲ እንዴት ቴስት እናደርግ ነው right so where x is equal to x represent x1 and x2 is the vector of binary component states we have binary components because they are parallel systems right binary component ባለሁለት ናቸው two component binary the objective is to determine our unreliability unreliable መሆናችንን ለማለት probability of x1 equal to 0 and probability of x2 equal to 0 why we take 0 because we are going to unreliabilities not to be happen we want to be 1 success right so probability of x1 equal to 0 and probability of x2 component 2 equal to 0 fail unreliability by using probability calculus we can express the probability in terms of the calculus form that is probability of x1 equal to 0 and probability of x2 equal to 0 equals probability of x2 equal to 0 under the condition where x1 equal to 0 times probability of x1 equal to 0 just we are expressing the probability of the two component systems to have unreliable results right unreliable results that's 0 right that's 0 and if we judge x1 if we assume or we decide x1 and x2 to be independent natural we can express the probability in terms of calculus or calculus distribution expression of the probability can say probability of x1 equal to 0 this probability the same this one is the same with this side the left hand side so equal to probability of x2 equal to 0 times probability of x1 equal to 0 which is different because we assume x1 and x2 is independent here is not the same right by specifying the probability of the probabilities assume probability of x1 to be 0 and probability of x2 to be 0 when x1 is 0 ይሄኛው ምን conditional probability ነው probability of x1 0 ብለናል probability of x2 0 ለመሆን ምን ያስፈልጋል x1 should be 0 that is we arrive on unreliability test both items cannot be the same so the marginal probability can be easily specified marginal probability means probability of x equal to 0 but the conditional probability means probability of x1 to be 0 when x1 is 0 that is conditional probability is difficult to confirm and it's very difficult to prove why marginal probability is easy to specify because we have sufficient data for x but we don't have sufficient data for probability for conditional probabilities we don't know x2 to be 0 when x1 is 0 under the condition where x1 is 0 so we do have limited data and such things is more difficult to specify the question is what to do about conditional probabilities the thing we want to check conditional probabilities conditional means this is posterior probability so what to do right so what to do if it is difficult to specify conditional probability ማለት ነው x2 0 ይሆናል መቼ x1 0 በሆነበት ማለት ነው conditional so what to do the first thing as a solution we can make direct assignment of probabilities we can assign probabilities directly based on our experience that is assigning probability means expressing uncertainty so about x2 equal to 0 given x1 ማለት እንችላለን assume መነሳት እንችላለን based on our prior experience but we have to model the dependency. ይህንን ካለ ኮንዲሽናል ፕሮባቢሊቲ እንደዚህ ካስቀመጥን በራሳችን ዳይሬክት አሳይመንት ካስቀመጥን ምን ይቀራል ማለት ነው? We should develop the model, right? Should develop the model. To do this or to develop the model, we have to identify the source causing or the most common cause. The most common cause that makes probability of x2 be 0 when probability of x1. What happened is that's a failure, right? Failure. Okay. So the dependency and specify proportion of failures due to common causes. So that's the probability x2 0 የሚሆንበት when x1 0 በሆነበት ከሆነ ሶርሱ ማወቅ ያስፈልጋል። Let's x is equal to 0 denote the event that the common cause occur. When the event, ስለዚህ ይሄ በሆነበት we can specify conditional probabilities as follow. Right? Probability of x1 equal to 0 and x2 is equal to 0. We can specify express probability of x1 equal to 0, x2 equal to 0 under the condition x equal to 0. That is probability times ይሄን ኤክስፕሬሽን መጠቀም እንችላለን ነው። Right? ይሄ ሞዴላችን ነው ወይ ደግሞ የሞዴል ዲስትሪቢዩሽን ነው። Right? So this probabilities ይሄን ስናስቀምጥ ግን we should remember that this probability can only occur where as condition, which means some causing factor happen that makes probability of x2 to be 0 when x1 is 0, right? x1 is 0. So suppose that the components of the same type, we have two component to x1 and x2. For example, two similar machine sample from huge stock of similar machines. Yan apply ልናደርግ ነው። ይሄን እዚህ ጋር ነው probability distributions we are going to apply. So we have to assume we took two machines from huge stock of similar machines. ለምሳሌ 100,000 ማሽን ሊኖር ይችላል ወይ 100 ማሽን ሊኖር ይችላል. We took two means here parameter equal to 2. If we have strong background knowledge, now we have we could put the conditional probability what? Probability of x2 equal to 0 when x1 is b0. Right? 0. So equal to probability of x2 is equal to 0. That is, we judge that x1 equal to 0 and x2 is equal to 0. Independent nature. As the information that x1 equal to 0 would not add much information relative to the knowledge already available. ስለዚህ በቂ knowledge ካለን ይሄን ኤክስፕሬሽን ማስቀመጥ እንችላለን። Just assign direct probability, right? Probability to test conditional probabilities. So that we have no knowledge now, sorry. ይሄ knowledge ባለበት በዚህ distribution ማስቀመጥ እንችላለን about the machine. ነገር ግን what if you don't have sufficient knowledge, right? And how to assign probabilities for the system functioning at a specific point in time? Or what would then be our unreliability probability of x1 equal to 0, probability of x2 equal to 0? ምን እናደርገው ነው? knowledge ባለበት ቀጥታ distribution እናስቀምጣለን። ነገር ግን we have limited knowledge or we have no knowledge about the distributions, so unreliability test will be difficult. Then how we can do this one? Right? Now we say here what would then be our unreliability probability of this is unreliability test 0 ነው ቼክ እናደርገው ፌደር ነው። So because we have no knowledge about the performance of these types of machine አናውቅም ሁለት ማሽን ነው ከመቶ ውስጥ አስቡ we would assign a failure probability of 0.5 እውቀቱ knowledge ከሌለ probability 0.5 ነው የሚሆነው which means half ነው you don't have knowledge it will be occur or reliability ነሳቸው ምንድነው we will give half 0.5 situations. That means the probability of x1 equal to 0, probability of x2 equal to 0 to be 0. A probability of both x1 and x2 0 ለመሆናቸው we will give half because we don't have any information. 0.5 probability from 1. if we judge x1 and x2 independent, it will give a system reliability. ስለዚህ x1 እና x2 independent ነው ካለ system reliability ምን ማለት ነው? 0.5 times 0.5 equal to 0.2. This is reliability, system reliability. ስለዚህ system reliability, which means probability both x1 and x2 to be 0 will be 0.25. That is unreliability test. System unreliability ወይም ደግሞ the system to fail is 0.25. It had a chance of 0.75 not to fail or to function. But given x1 equal to 0, we should change x1 0 we should change, or we have to increase our probability of x2 equal to 0. x1 0 ከሆነ ስለዚህ x2 it have the higher probability to be x2 to be 0, that is to fail, right? And we have received information about the performance of these types of machine, right? Now the question is, how should we incorporate this in our analysis? This means how we can increase the probability of x2 to be equal to 0 when x1 is 0. Situation where x1 is 0, which means x1 is known, that is fair, and x1 is unknown to be 0. We have to increase. Now how we can incorporate in our analysis? Now let's take an example. Let's P, this one, be a proportion of P means its probabilities, right? The proportion of a machine that are not functioning, which is unobservable quantity. P, observable quantity, no, it's not probability, sorry. It is observable quantity. That means proportion of machine not working or not functioning. If we have no information about the performance of the machine, we don't have an information, we could specify uniform prior distribution as we did before. So the manak 0.5 probability set over the interval between 0 and 1. 0.5 set but 0 na ban makan to express our uncertainty about the value of P. Now, if you have some knowledge about the value of P, the proportion of machine that doesn't work, we could assign probability of the component I. Component I naskental the third thing. So we do have x1, x2, and we are adding component x, another component I የሚባል አስቀመጥን third. ለዚህ third component ከሆነ we should just the components are independent. አሁንም x1 አለን x2 አለን just x1 x2 ቫልዩ ያስፈልጋቸዋል third component አመጣ ስለዚህ distribution ማለት ነው 100% divided by 1 divided by 3 we will get 1 over third unreliability system ሶስተኛ አካል ስለመጣበት ማለት ነው which is higher than 1.4 obtained by judging x1 and x2 to be dependent. Here 1.4 means this value 0.25, right? These values. So the ሶስተኛ component known values ስናመጣ our probability increase about 0.33 than 0.25. Now we are seldom in a situation with no information. ለዚህ ችግሩ ይሄ ነው analysis ብዙ ጊዜ ካለ ኢንፎርሜሽን አንሰራ ስለዚህ ያየነው ምንድነው it is more of theoretical. Why is it theoretical? Because we want to give some illustration about the importance of precise understanding of information, observable quantity, and uncertainties. ያየነው አሁን with no information ነው which አብዛኛውን በኢንፎርሜሽን ቤዝ ነው የምንሰራው right? ዋናው ዓላማው ግን the importance of having information, observable quantity, and assigning or measuring uncertainties and assigning probabilities ለማሳየት ነው ነው. Now, we suppose that the machine we are studying in a specific operational and maintenance environment. አሁን ሌላ ኬዝ መጣ አሁን የምናጠናው ማሽኖች ነበሩ ቅድም ሁለት ማሽን ነው የወሰድነው from large stock of machines አሁን ግን ምንድነው we get some information that is specified operational and maintenance environment ያውን ደግሞ አንድ ማሽን ምን አለ maintenance ላይ ያለ ማሽን ነው ሶስተኛ which is not random which means it is not taken from a population of similar machine ቀደም ሁለት ስንወስድ ተመሳሳይ ባህሪ ካላቸው ነው። አሁን ግን ሌላ አንድ ስናነሳ ምንድነው it has maintenance case ሌላ የተለየ መረጃ አለው ማለት ነው። ስለዚህ this machine doesn't reflect total population. Now the question is how should we then proceed? በአጋጣሚ ካነሳናቸው ውስጥ ሁለት አስና መጀመሪያ ሶስተኛ ስናነሳ ሜንቴናንስ ኢሹ አለበት። So in such case we do not introduce fictional population and quantity. Fictional means just distribution of fictional is just እንደለቦዳገ ወይም ደግሞ ከፕራዮር ዲስትሪቢዩሽን ወይም ከሂስቶሪካል ዳታ ወስደን የምናስቀምጠው አይደለም ነው። rather we have to consider different value of p. የp proportion አሁን different value for describing our uncertainty about the occurrence of I xi to be 0, and we are confident we have p for being able to predict xi. P means the proportion of machine functioning is reflected by the uniform distribution. For example, specifying proportion of the proportion of machine that are not functioning equal to 0.1 means in specific other that we'd be fairly sure that no machine failure occur if p equal to 0.6. It's more than half. I think you understand what I mean. ለምሳሌ the proportion of machine fails when not functioning, that is we are going to test unreliability measures 0.1 ነው ካለን and if we get probability of 0.6 it's far 0.5 more than the value predicted values ማለት we can say at least there will not be predicted we can predict one machine failure out of 2. ይሄ 0.6 ሆነ more than half ነው ከhalf በላይ። ስለዚህ ሁለት ካለ ከሁለት አንድ ፌል ሊያደርግ ይችላል ማለት ነው። ይሄኛው ግን less than right it's less than 1, which means there will no machine failure, which is far less than the uniform value of p, right? That uniform value or uniform probability means 0.5 for each, right? 0.5 for each. Now, this distribution is not such important. I would like to I would like to see another issues. Important, right? Now, in addition to the method we use, we can also determine reliability analysis using sensitivity analysis. And sensitivity analysis, right? Just we take extreme cases, right? Extreme cases, and by changing the input probabilities, we can determine the unreliability tests. Sensitivity analysis already chapter 1 or chapter 3 right? Just we have different scenarios. We give probability 0.1, the first case. Maybe we give probability of the system not function 0.50, another case, or we will give probability is equal to 0.99. Different scenario set, we are going to evaluate unreliability test, where we are going to see what if we made a small change, right? Small change. Now let's go to the other one, or the other reliability test, the so-called structural reliability analysis. Is structural more in terms of y equal to x alpha plus beta of x, or in terms of model ሲገለጽ ወይም ደግሞ more than one variables ሲኖሩ ማለት ነው, right? Or we have a models, right? We have a models. Now let us consider how to apply structural reliability tests. Let us consider the load strengths. Example, load strengths, where the limit state function is given by, and the load strengths ለማየት ነው እና ባቴ መንገድ ሊሆን ይችላል ያስፓልት ሊሆን ይችላል, and we determine the load strengths in terms of function as follow. We say y equal to load strengths g times of x. G of x means this is a model, right? This is a model, and x1 minus x2. x1 represent strengths or measurement of strengths of the system, and x2 refers load measurement, right? Which means x1 and x2 represent a strengths measure of the system and load measurement. Strengths ነው x1 strengths ነው, x2 ደግሞ load measure የምናደርግበት ነው። And G is the model expressed uncertainty of x1 x2 ሞዴሉ uncertainty ነው የሚገልጸው። ያው እንግዲህ ሞዴል ማለት uncertainty መግለጽ ማለት ነው using density function f. System reality can be expressed one. This one is not. We are dealing about probability of y less than 0, which means less than the load strengths. Basic functional distribution. Here distribution, don't care about these distributions. It's enough only to say density function. A density function, right? Now, one such distribution, that is density function distributions, F could be multivariate, bivariate, normal distributions, with parameter of mean, standard deviation, and this is the correlation coefficient. With just the value of x and x2, suppose we have strong background knowledge about the value of xi. Xi means x1, x2. For example, corresponding to 20 observation, xi, xij, that all are coincident relevant for xi. ምሳሌ መረጃ አለን ማስ xi present by 20 observations, which means x1 equal to 5, x2 6, some observation አለ 20 observations አሉ ማለት different number or the same number, and this observation may be mean, maybe standard deviation, or maybe correlation coefficient. That is all about our choice, which express our distribution. Then we may use fixed value of the parameter, the mean, standard deviations, or the correlation coefficient values, right? Values. Now, suppose we do not have such background information. That is bad. We don't have information, and we will like to update our prediction and uncertainty assessment when the new data become available. እዚህኛው ላይ ዳታ ባለን ነው ወይ የሚን ወይ ስታንዳርድ ዲቪዬሽን ወይም ደግሞ የኮሬሌሽን ኮኤፊሺየንት ባለን ሰዓት ነው። ከሌለንስ we don't have background information. Background information means historical information, but we obtain new data. At this data we obtain right now. That new data, based on this new data, we are going to determine posterior distributions. In this case, we would adopt the full Bayesian procedures. ለምን ነው የምንጠቀመው? Bayesian procedures, posterior distribution based on prior distribution is going to determine posterior distributions. Our posterior distribution is the distribution of mean, standard deviation, or the correlation coefficients, or the value of p, any number that we have at hand. So there is a Bayesian procedure, we have to assign probability v, express uncertainties, like that. Different procedures we have been discussed. So there is this no true value of parameter. Bayesian ሁሌ ማስም ያደርገው ምንድነው? There is no true value of parameter, which means whether we use overall distribution or the mean value or standard deviations, the parameter is not true. Not true unless they are observable quantities. That is the important thing, right? And the prior and posterior distribution is uncertainty distributions. Prior ቀድሞ የነበረው posterior distribution computational distribution is uncertainty distribution, which means there is uncertainty in all type of distributions, whether historical or expected distributions. So the prior or the posterior distribution express our confidence. That is important thing in the parameter values being able to predict. Prior distribution when the posterior distribution በማየት we will have confidence on the value of the parameter we are going to estimate. The parameters are the value of the mean or observations, which is to estimate future outcomes. The outcomes may be x or maybe y. That is the right and the left-hand side, right? The performance or performance indicators or factors that affect our performance. Now let's Y be the true rest capacity of the system. The system capacity at the time of interest when taking into account the load. Y is the true capacity of the system. Well, that is the load, right? Taking into account the load. Using the model, we already expressed the model function in terms of model g of x equal to x1 minus x2. I think you remember we have seen it. We have put y equal to g of x. That is, this is we express in terms of model. Y equal to g of x. Y is a function of x. This means a simplification, or this means a simplification, and in structural reliability analysis, it is common to introduce an error term. Model sincera, structural equation we often consider the error term E because there are unknown factors that affect Y, right? So such thing Y equal to xi, x0 times xi minus x2, x naught represented by the error term. This gives a better model. Why it is better model? Because we assign assumptions, or we give assumptions for the items which are not included in the model, right? In the model. Now for simplification, we judge x naught and x1 minus x2, right? Strength and load to be independent, which means the error term should be independent of the factors, of the load factors. This means our uncertainty about the ratio between the true capacity y and the measured capacity x naught equal to y divided by x1 minus x2, the strength and load factor, is not influenced by the value of the capacity indicators. Capacity indicators are both the strength and the load, right? The load. Now this, by specifying functional distribution, we use functional distributions for the x naught, that is the error term, and x1 minus x2, the strength and load, we arrive at uncertainty distribution of y. The error term and the factors of the loads or strings, we can determine the value of y. How we can determine? We have to estimate the model. Estimation as well. Estimation using software, not manual. If we use the means as a predictor, mean in the predictor, the true capacity is predicted by what? Mean of x naught, that is the error term, and mean of x1 minus mean of x2. Mean value. If you use standard deviation, we can change this into standard deviation. So by introducing the error term, the uncertainty in y increase. Yes. Error term in model we have to increase the uncertainty of y because we consider unknown figures. There are factors which are not included in the model but affect y. So in structural reliability analysis application, the application of this model, we call it model uncertainty. Y uncertain, we call it model uncertainty. If the value of y is uncertain, we call it model uncertainty. The uncertainty of y should increase by including the constant, the error term. If we use the model x1 minus x2 to express uncertainty about the true capacity y, this means our analysis is conditional on the use of this model. That is good. አሁን ደግሞ x1 strength እና load factor load measurement uncertain ከሆነብን data what ምን ማለት ነው? So our analysis is under conditional, which means y equal to g of x is conditional, right? Conditional. We must often assume that parameters x1, x2 should be observable. There should not be an uncertainty on the parameter. Because we have to give parameter like uncertainty, we are dealing about conditional models, right? If we find the model X1 and X2 is not sufficiently accurate for its purpose, we will improve the model. X1 and X2 modelun አይገልጹትም ካልን we have to improve the model. Improve the model means use other appropriate or relevant data or relevant factors. Right? Relevant factors. I almost to finish. I need only 2 minutes. So using the equation y equal to x naught, this is the error term times x1 minus x2, the strength indicator and load indicator, give an accurate model. But to express uncertainties in this case, we need to simplify and use independence. That is the most important thing. A model accurate now, accurate when there is independence between x1 and x2, as we have mentioned before. There should not be dependence between the factors that affect y. Now the challenge is it may be difficult to find relevant data to support uncertainty analysis of x. አስቸጋሪ ነው። ኤክስ ኖት ወይም ደግሞ ኤክስ ኖት ያልነው ማን ነው? the error term ነው። error term used to capture the variables which are not included in the model. ይህንን መግለጽ አንችልም because we don't have data for undetermined variables, right? Undetermined. Thus, we can say that the expression y, g of x, x minus 1, under the x naught, that is the error term, we can say certain. Uncertainty improve about the error term. If we had a strong database for y, about y, we could make a direct assignment of distribution of y. Value we don't need to go this process. We don't need to talk about x naught, x1, x2. We can directly apply. And there will not be need for modeling. Modeling so when you model we don't have strong data and we are uncertain about the value of y, right? The value of y. This is all about structural reality analysis, and the final PowerPoint is about what should be considered or why need to go beyond probabilities. Only one slide, right? I'm going to finish. So assigning probability by itself is not enough. So we need to see beyond probabilities. For example, a probability assignment that is stated as probability of A condition for K. K means that is the knowledge we have or the parameter. Or a probability of an event given the background knowledge of K. Probability of A means we are computing the probability of A based on background knowledge of K. And K incorporates different assumptions. ብዙ assumptions incorporate እናደርጋለን K ወይም ደግሞ parameter measures እናደርጋለን. Assumptions are a part of K. Hence, we need to see beyond probability numbers when assessing risk. Because we start from assumption about K, and the probability is determined based on the assumed K or assumption of K, we have to go beyond probabilities because K has doubt or some limited informations. Or our assumption may not be right. So, in risk analysis, we must address factors that can cause surprise, right? Right? Surprise relative to the probabilities and expected values. So, as a risk analysis, you have to consider some surprise. Some surprise means out of our assumptions, out of K, observed values. So, risk quantification often required a strong simplification. That is important thing. Risk analysis, we have to have strong simplifications, strong assumptions, which leads to ignore or give too little or too much weight for important factors. That is the basic in this chapter, right? In this chapter. So you must have strong simplification, strong assumption. This help you to avoid to give much probability for irrelevant or low probability for very relevant things. As a result, probability assignment do not reflect or relevant and uncertainties. That is important thing. Why we go beyond probabilities? Because assigning probability for uncertainty doesn't reflect or relevant issues about the uncertainties, right? For instance, if we consider 1,000 throw, we just throw a coin, we would be quite sure that the proportion of heads, right? The proportion of heads which do not by P will be close to 1/2 or half. Just something በኖረው head when the more tail the more we have to 50%. But it's not accurate. Most people would assign very low probability for observing, say, less than 100 heads. Yeah, assign ሊያደርጉ ይችላሉ። ለምሳሌ ከአንድ ሺህ ውስጥ ለመቶ ብቻ that is 10% ሊያደርግ ይችላል። So that we have to go beyond probabilities. Thank you. This is the end of chapter 4.
ልዩነት መፍጠር ዓላማችን ነው። ዓለም አቀፍ ተወዳዳሪ መሆን አለባችሁ። የናሽናል ኤርዌይስ እህት ኩባንያ ናሽናል አቪዬሽን ኮሌጅ ጥራትና ደረጃውን የጠበቀ ስልጠና በመስጠት ብቁ ዜጋ እያፈራን ነው። በፍላይት ኦፕሬሽን፣ በበረራ መስተንግዶ፣ በቲኬቲንግና ሪዘርቬሽን፣ በሆቴልና ቱሪዝም ሙያዎች አሰልጥነን ተወዳዳሪ እናደርጉታለን። ኮሌጃችን ካናዳ ከሚገኘው ኢንተርናሽናል ኤር ትራንስፖርት አሶሲዬሽን አያታና ከእንግሊዙ ICM ጋር በመተባበር ዓለም አቀፍ ዕውቅና ያለው ስልጠና እየሰጠ ይገኛል። በፍላይት ኦፕሬሽን፣ በበረራ መስተንግዶ የምንሰጣቸው ስልጠና ከኢትዮጵያ ሲቪል አቪዬሽን ባለስልጣን ሙሉ ዕውቅና አለው። አድራሻ ከጎላጉል ታወር 22 አደባባይ ወደ ሾላ በሚወስደው መንገድ ላይ የናሽናል ኤርዌይስ እህት ኩባንያ ናሽናል አቪዬሽን ኮሌጅ ህልሞን